Okay, this will be our lesson on section 6.2, and this involves the utilization of the Laplace transform technique for solving second-order differential equations. First, to introduce this, the idea of Laplaces of derivatives. Section 6.2 does the derivations of these and shows the proofs, but I'm just going to cut right to the chase. If we do the Laplace transform of a first derivative of a function, that's going to turn out to be s times the Laplace transform of the function minus f naught, whatever the initial condition is for f, all right? Now, you can derive this pretty easily, and the derivation for it is in section 6.2. We're not going to spend time on the derivation now because I want to show you how to apply this. In the same respects, there is a Laplace transform for a second derivative of a function. The Laplace transform of f double prime is equal to s squared Laplace transform of f minus s times the initial condition f naught minus f prime of naught, the initial condition of the first derivative, right? Once again, the proof of that is in section 6.2. So if you're interested in where these came from, be my guest to read through those derivations. What we're going to do is apply these, though, and you can see what they do. If we apply the Laplace transform to a second order differential equation, what it's going to allow us to do is replace the first and second derivative terms with basically algebraic expressions. The Laplace transform of f is going to be a new function in s. And of course, the initial conditions will generally be given for these. That's actually one of the advantages of using the Laplace transform technique for solving ODEs. First and foremost, you don't have to sort of solve the equation twice because you don't need a homogeneous solution first. And the second thing is you don't plug in the initial conditions at the end of the problem after you've solved it in general. The conditions are actually part of the solution, so you go straight to the specific solution every time. Okay, we're going to first do this in general. So we're going to solve the differential equation y double prime plus a y prime plus b y is equal to r of t. So these are first derivatives with respect to time and second derivatives with respect to time. This isn't a dy dx, this is a dy dt because r is a function of t. As you can see, this is a non-homogeneous second-order differential equation, and these coefficients here could be constants or functions. Notice it's in standard form. This also is a special kind of differential equation where this represents the function input and the solution is the output. So r of t is referred to as the input of the equation, and the solution y of t is referred to as the output. These are enormously common equations in this form. I think when we looked at circuits and harmonic motion, they were both in this form. Okay, well, here's the Laplace transform technique. I'm going to begin by taking the Laplace transform of this entire equation. So on the left-hand side, that's going to be the Laplace transform of y double prime plus a times the Laplace transform of y prime plus b times the Laplace transform of y is equal to the Laplace transform of r. Now, just as we did in the last section, we're going to use the standard that the Laplace transform for any function like y, we just replace that with capital Y. This will be y of s, whereas this was y of t, so it's going to do the variable transfer as well as the function transfer. In the same way, the Laplace transform of r, we're going to replace that with capital R. So let's make those substitutions right here. I'm going to also substitute in what these guys are equal to. So you'll see me write two lines. The first is just going to be the substitution of the forms of the first and second derivative, and then I'll write it again where I use the substitution for the Laplace transforms of r and y. So first, we're just going to replace this first term with all of this. So that's going to be s squared times the Laplace transform of y minus s times y naught minus y prime naught. That takes care of the first term. Second term is going to be a times this whole thing. So that's going to be plus a times s, the Laplace transform of y, minus a times y naught. And then the last thing is just by. So that's going to be plus b times the Laplace transform of y, and then that whole thing is going to be equal to the Laplace transform of r. So all I did there was just substitute in what the first and second derivative of the Laplace transform is. Now I'm going to go ahead and make these substitutions to make it algebraically a little bit simpler. I'm also going to combine some like terms. So the Laplace transform of y exists here, here, and here. So I'm going to factor out s squared plus as plus b, and all that's times the Laplace transform of y, which I'm going to go ahead and substitute in y. Everything else I'm going to put on the other side, and everything else is negative s times y naught. Over here it'll be positive s y naught, and there's negative a y naught. Over there it will be a y naught, so that's s plus a times y naught. There's a y prime of naught, that'll be positive over here, y prime naught. And then finally, r is already over there, so plus capital R. Okay, the last step then, in order to solve for y, and remember, y is the Laplace transform of our solution. So if we can solve for y as a function of s, all I have to do is apply the inverse transform to it, and then it will become my function y, all right? So first we got to divide through, so y of s, just to remind us it's a function of s now, will be s plus a times y naught plus y prime naught plus r, and all that's over this factor s squared plus as plus b. Okay, well now we're going to invent a function to represent this. The function is q, and q is going to equal 1 over, in this case it's this, s squared plus as plus b. This thing is called the transfer function, and I'll show you why in just a second. So it's the transfer function. And if I go ahead and make the substitution, this entire denominator just turns into q in the numerator. So that means y is then going to be equal to s plus a times y naught plus y prime naught, all of that times q plus rq. In the unique case where y naught and y prime naught are 0, and that's super common. We very often run into initial conditions for second order equations that are those conditions. They don't have to be. This actually is our general algebraic solution, but it could turn out to be simpler if y naught is equal to y prime of naught is equal to 0. Then y is just equal to rq. And because of that, that means q is then equal to y over r. And let's look at what that means, y over r. Remember, y is the Laplace transform of the function y, which is also called the output of the function. So it's the Laplace transform of the output over the Laplace transform of the input. And that's why they call q the transfer function, because it transfers from output to input. It's always of this form, that is, q is always going to be 1 over s squared plus as plus b. And you notice that that always comes from the original differential equation. So the interesting thing is the transfer function is not a function of either y or r. It's simply a function of the original differential equation's coefficients. So you can build q very easily just by looking at the equation. We'll be using this equation anytime the initial conditions aren't 0, because there's the place where you plug them in. But you can default to this anytime the initial conditions are 0. So scan the question first, and it'll tell you which one of these two you have to use. All right? Once you reach this point, then, one of these two is then going to give you the solution. And how are you going to find it? Well, if y is equal to the Laplace transform of our solution, then our solution is equal to the inverse Laplace transform of y. So that means we have to take this guy right here, and we have to find a set of functions that it sums to that are all easily recognizable Laplace transforms of functions. So it's very much like function matching. You'll be taking this algebraic solution and a good table of Laplace transforms, and you'll be figuring out what this is the sum of in terms of Laplace transforms, and those will then give you the solutions for y. That will be the specific solution for these initial conditions. It will not be a general solution. Frequently finding that solution, because the form they take frequently looks like this, and therefore you're going to have to decompose partial fractions to turn this into a sum of individual rational expressions instead of one big rational expression. Otherwise, you'll never recognize the individual Laplace transforms that the sum actually represents. All right? Consequently, as we work through our first example problem, and then you guys work your own homework problems, you're going to have to be pretty good at the technique of partial fraction decomposition, because doing this process, that is recognizing in this function where those inverse Laplace transforms are, is entirely a process of partial fraction decomposition. So one of my videos tonight will actually review that process.